Welcome to Organic Chemistry, Principles and Mechanisms by Joel Karty. Chapter 11, Electrophilic Addition to Nonpolar Pi Bonds, Part 1. In the previous three chapters, we focused on four closely related mechanisms, SN2, E2, SN1, and E1 reactions. In Chapter 11, we will apply the same types of analyses to electrophilic addition reactions, where an electron-deficient species accepts electrons from a pi bond to form a new sigma bond. The addition of a hydrogen halide to a carbon-carbon pi bond is a two-step process. In the slow first step, the alkene is protonated by a strong acid to generate an intermediate carbocation. This cation then coordinates with the anionic conjugate base to give the haloalkane product. In the prior slide, it was noted that the first step in the electrophilic addition reaction is the slower rate-determining step. This is logical for two reasons. First, one pi bond and one sigma bond are broken, but only one sigma bond is formed in this step, so the net enthalpy of the step is positive. Second, the products of the first step are a carbocation and a chloride anion. Two charged species have been generated, and the carbon bearing the positive charge lacks a full octet. We would expect the intermediate to be higher in energy than the reactants, leading to a relatively high transition state energy. In the second step of the addition, a new sigma bond is formed and the charges are eliminated, leading to a product that is more stable than the intermediate. This exergonic step would be expected to have a relatively low transition state energy. Note that the product of an addition reaction is typically lower in energy than the reactants. This reflects the replacement of one sigma bond and a relatively weak pi bond with two new sigma bonds. Although the addition of strong acids to carbon-carbon pi bonds is typically an exothermic process, there are instances where the reaction does not take place. One such instance is when the pi bonds are in a benzene ring. Benzene does not undergo electrophilic addition reactions because the pi bonds in the ring are extremely stable. The stability of the pi bonds in the benzene ring are due to a phenomenon called aromaticity, which will be discussed in more detail in Chapter 14. The benzene ring can be drawn with two equivalent resonance structures, indicating that the pi electrons are fully delocalized about the ring. The addition of an acid across one of the double bonds would disrupt this delocalization, eliminating the stability due to the resonance. When asymmetrically substituted alkenes undergo electrophilic addition, two products are possible. For example, when propene is reacted with hydrogen chloride, 1-chloro and 2-chloropropane are produced. 2-chloropropane is the principal product in the reaction. In the major product, the hydrogen has added to what was the 1 position in the starting propene. This type of regioselectivity is typical for asymmetrically substituted alkenes. The principle is called Markovnikov's rule and states that the proton addition step in an electrophilic addition to an alkene will occur at the carbon that has the most protons. Exceptions to Markovnikov's rule are frequently observed. These are called anti-Markovnikov additions. The mechanistic basis for Markovnikov's rule relates to the cationic intermediate formed in the reaction. The addition of the proton to the terminal carbon of propene leads to a secondary carbocation intermediate, while addition to the internal carbon leads to the less stable primary carbocation. Since the proton addition step is endergonic, following the Hammond postulate, the transition states for each proton addition will resemble the intermediate, and the addition leading to the most stable intermediate will have the lower energy barrier. Since this type of addition reaction involves a cationic intermediate, there is the potential for a cationic rearrangement to occur if it leads to a more stable intermediate cation. In the case of 3-methyl-but-1-ene, the addition of hydrogen chloride leads to a 1-to-1 mixture of 2-chloro-3-methylbutane and 2-chloro-2-methylbutane. The 2-chloro-3-methylbutane is the expected product from Markovnikov addition. 2-chloro-2-methylbutane is formed when the intermediate secondary carbocation undergoes a 1,2 hydride shift to generate a more stable tertiary carbocation, which the chloride ion then adds to. The rate of hydride shift is competitive with the chloride addition, so a significant amount of the rearrangement product is formed. Stereochemistry in electrophilic addition reactions is dependent on the symmetry and structure of the starting alkene. For example, the reaction of 1,2-diphenylethylene with hydrogen bromide produces 1-bromo, 1,2-diphenylethane, which has 1 chiral center. The product is produced as a racemic mixture of the R and S enantiomers. The reaction of deuterium bromide with cyclohexene follows the same mechanism as the reaction using hydrogen bromide. However, this reaction generates 2 stereocenters, and therefore 4 stereoisomers are possible. In fact, all 4 stereoisomers are generated in the reaction. If we examine the reaction with the cyclohexene edge on, the pi electrons can form a bond with the deuterium either above or below the ring, with equal likelihood to generate the intermediate cation. Subsequent attack by the bromide can also occur equally from above or below, leading to equal amounts of all 4 stereoisomers. The treatment of an alkene with a weak acid like water leads to no reaction. The low concentration of hydronium makes it very difficult to form the cationic intermediate in the addition reaction. Also, the fact that alkenes in water are generally immiscible also inhibits their reactivity. If the reaction between an alkene such as 1-butene and water is conducted in the presence of a strong acid, an addition does take place across the double bond in a reaction called acid-catalyzed hydration. The product of the reaction is an alcohol. Note that only a catalytic amount of strong acid is required for the reaction to proceed in high yield. In the acid-catalyzed hydration mechanism, the first step is essentially identical to the addition reaction for hydrogen halides. Hydronium, generated by the reaction of water with a strong acid, protonates the alkene to generate the most stable cation. In this case, the secondary cation is formed. Although water is a relatively weak nucleophile, the relatively unstable cation will rapidly react with it. Another molecule of water deprotonates the product to form the alcohol and regenerate the hydronium catalyst. Typically, sulfuric acid is used to catalyze the reaction. As well as being a strong acid, the bisulfate conjugate base is a much weaker nucleophile than water. Alcohol can be used instead of water for this reaction. If an alcohol is used, the reaction is called an alkoxylation rather than a hydration, and the product is an ether. The mechanism for the reaction, however, remains the same.